Okay, so good afternoon to all of you, students of CS6201. So again, welcome to our virtual class for computer organization and architecture. So our topic for today is about memory location and addresses. So this is week 6. So the memory location and its addresses in computer organization. So the memory locations and addresses determine how the computer's memory is organized so that the user can efficiently store or retrieve information from the computer. The general purpose computers nowadays have 32 to 64 bits. So the computer or the group of 8 bits called a byte. So the computer's memory is made of a silicon chip, so which has millions of storage cell. So where each storage cell is capable to store a bit of information, so which either a value of zeros or ones. So what is memory location in computer organization? So each memory location in a stored program computer holds a binary number or decimal number of some sort. So its interpretation as data of some data type or as an instruction, and used or determined by the instructions which retrieve and manipulate it. So but the fact is computer memory holds instructions and data, and a single bit is very small to hold this information, so bits are really used individually. So as a solution to this, the bits are grouped in fixed sizes of n bits. So the memory of the computer is organized in such a way that the group of these n bits can be stored and retrieved easily by the computer in a single operation. So the group of n bit is termed as word. So where n is termed as the word length. So the word length of the computer has evolved from 8, 16, 24, 32 to 64 bits. So the general purpose computers have 32 to 64 bits. So the group of 8 bit is called a byte. So now, the memory words. So whenever you want to store any instruction or data, may it be or a byte or a word, you have to access a memory location. So to access the memory location, either you must know the memory location by its unique name, or it is required to provide a unique address to each memory location. So the memory locations are address from 0 to raised to k negative 1. So like for example, a memory has 2 raised to k addressable locations. So and thus the address space of the computer has 2 raised to k addresses. So let us try some suitable values for k. So we have 2 raised to 10 is equals to 1k or kilobyte. 2 raised to 20, so equal to 1 M or megabyte. So 2 raised to 30 is equals to 1 G or 1 gigabyte. 2 raised to 40, it's equal to 1 T or terabyte. So the byte addressability. So till now, we have gone through 3 information storing quantities, the bit, byte, and word. So as a solution, most modern computers assign a successive addresses to successive byte locations in memory. So this assignment of addresses to individual byte location is termed byte addressability, and memory is referred to as byte addressable memory. So the assignment of byte addresses. So we have the little endian, like in DEC and Intel. So in little endian, we have the low ordered byte stored at lowest address. So we have byte 0, byte 1, byte 2, byte 3, or the memory location address. So we have the 32-bit data like 46, 78, 96, and 54. Okay, so from a high order bit to a low order bit. So as you can see, we have the memory location address and its value. So starting from the 8000, the memory address, and its value is 54. So 8001 and its value is 96. 8002 and its value is 78. And 8004 and its value is 46. So in big endian, so we have in IBM, in Motorola, Sun, and HP. So big endian, high order byte stored at lowest address. Okay, so we have byte 3, byte 2, byte 1, and byte 0, the memory locations. So the programmer's protocol should be careful when transferring binary data between big endian and little endian machines. So the two ways in which byte addresses are assigned. Okay, again, in big endian and little endian assignments. So there are two ways. Okay, so in big endian, lower byte addresses are used for the more significant bytes of the word. Okay, so in big endian byte order, the most significant byte, the big end of the data is placed at the byte with the lowest address. So the rest of the data is placed in order in the next 3 bytes in memory. Whereas in little endian, lower byte addresses are used for the less significant bytes of the word. So little endian byte order, the least significant byte, the little end of the data is placed at the byte with the lowest address. So the rest of the data is placed in order the next 3 bytes in memory. So in the given figure, the big endian and little endian assignments in byte addresses. So the big endian and little endian are two methods of assigning byte addresses across the words in the memory. So in the big endian assignment, the lower byte addresses are used for the leftmost bytes of the word. So observe the word 0. So in the image, so the leftmost bytes of the word have lower byte addresses. So in the little endian assignment, the lower byte addresses are used for the rightmost bytes of the word. So observe the word 0 in the image. So the rightmost bytes of the word 0 has lower byte addresses. So the leftmost bytes of the word are termed as most significant bytes, and the rightmost bytes of the words are termed as least significant bytes. So thus the big endian and little endian specify the ordering of bytes inside a word. So similarly, the bits must be labeled inside the byte of a word. And the most common way of labeling bits in a byte or word, okay, using labeling the bits, okay, so as by like B sub 7 or B6 or up to B sub 0. So from left to right, as we do in little endian assignment. So in labeling bits within a byte, like for example, we have a 32 bits. Okay, so the memory locations we have from 0 to 31. So B sub 0 up to B sub 31. So consider a 32-bit integer in hexadecimal. 0, x, 1, 2, 3, 4, 5, 6, 7, 8, which consists of 4 bytes. So 12, 34, 56, and 78. So this integer will occupy a 4 bytes in memory. So assume we store it at memory address starting 1000. So on little endian, memory will look like this. So it's address, memory location, and its value. So the memory address starting from 1000 and its value is 78. 1001 and its value is 56. 1002, the value is 34. And 1003, the value is 12. So a little example on little endian. So on big endian memory will look like this. So the memory address starting from 1000 and its value is 12. 1001 is equals to 34. 1002 is equals to 56. And 1003 is equals to 78. So another example, how is a 32-bit pattern held in the 4 bytes of memory? So there are 32 bits in the 4 bytes and 32 bits in the pattern. So, but a choice has to be made about which byte of memory gets what part of the pattern. So there are 2 ways that computers commonly do this. So using the big endian and the little endian. So in these definitions, the data, a 32-bit pattern. So it's regarded as a 32-bit unassigned or unsigned integer rather. So the most significant byte is the one for the largest powers of 2 raised to 31, up to 2 raised to 24. So the least significant byte is the one for the smallest powers of 2. So 2 raised to 7 up to 2 raised to 0. So for example, say that the 32-bit pattern, the 0x1, 2, 3, 4, 5, 6, 7, 8 is stored at address 0x004, 00000. Okay, so the hexadecimal. So the most significant byte is 0x12. The least significant is 0x78. So as you can see in the given figure. So within a byte, the order of the bits is the same for all computers. So no matter how the bytes themselves are arranged. So the word alignment. So words are said to be aligned in memory. So if they begin at a byte address, that is a multiple of the number of bytes in a word. So in a machine with word length, like for example, a 32-bit, the word boundaries occur at the bytes addresses 048. So it is said that the word has aligned addresses if they begin with the byte address that is multiple of the number of bytes present in that word. So for example, the word address 4 has 4 bytes in it with byte address 4, 5, and 6. So the word address 4 starts with the byte address 4. So which is multiple of the number of the bytes in word 4. So another example, if the word length is 16, which is 2 bytes, aligned words begin at byte addresses 0 to 4. So if the word length is 64, which is 2 bytes, aligned words begin at byte addresses 0816. So words are said to have unaligned addresses. So if they begin at an arbitrary byte address. So in case if the word address begins with the arbitrary byte address, the word is said to have unaligned addresses. So but conventionally, the words have aligned addresses as this lets the access of memory operand more efficiently. So this is all about the memory locations and how they are addressed to store and retrieve the instructions or data more efficiently. So with the memory addresses, it becomes easy to identify a specific memory location. So in case of 16-bit data, aligned words begin at byte addresses of 0 to 4. So in case of 32-bit data, aligned words begin at byte address of 048. So in case of 64-bit data, aligned words begin at byte addresses of 0816. So in some cases, words can start at an arbitrary byte address. So also then, we say that words locations are unaligned. So if we assign an address to individual byte locations in the memory like 0, 1, 2, 3. So if the word length of the machine is 16-bit, then the successive words are located at the addresses 0 to 46. So where each word would have 2 bytes of information. So similarly, if we have a machine with a word length of 32-bit, then the successive words are located at the addresses of 0, 4, 8, and 12. So where each word would have 4 bytes of information, and it could be stored or retrieve 4 bytes of instruction or data in a single and basic operation. So accessing numbers, characters, and the character string. So a number usually occupies 1 word. So it can be accessed in the memory by specifying its word address. So similarly, individual characters can be accessed by their byte address. So there are 2 ways to indicate the length of the string. So first, a special control character with the meaning end of string. So can be used as the last character in the string. Second, a separate memory word location or register can contain a number indicating the length of the string in bytes. So the memory operations. So today, general purpose computers are used a set of instructions called program. So to process data. So a computer executes the program to create output data from input data. So both program instructions or data operands are stored in memory. So to execute an instruction, the processor control circuits must cause the word or words. So containing the instruction to be transferred from the memory to the processor. So operands and results must also be moved between the memory and the processor. So the 2 basic operations involving the memory are needed. So namely, read and write. So the 2 memory operations are load, okay, or load operation for read and fetch. So the contents of specified memory location are read by the processor. So whereas the store operation or write, the data from the processor is stored in specified memory location. So the load operation transfers a copy of the contents of a specific memory location, so to the processor. So the memory contents remain unchanged. So the steps for load operation. So first, the processor sends the address of the desired location to the memory. Second, the processor issues read signal to memory to fetch the data. Third, the memory reads the data stored at that address. And fourth, the memory sends the read data to the processor. So the store operation transfers the information from the register to the specified memory location. So this will destroy the original contents of the memory location. So the steps for store operation are: first, processor sends the address of the memory location where it wants to store data. Second, processor issues write signal to memory to store the data. And third, content of register, which is the MDR, is written into the specified memory location. So the instruction set architecture. So it is a complete instruction set of the processor. So the instruction set architecture, also called computer architecture, it is an abstract model of a computer. So a device that executes instructions described by that ISA, so such as a central processing unit, is called an implementation. So the four types of operation. So we have the data transfer between memory and processor register, the arithmetic and logic operation, program sequencing and control, and the I/O transfer. So the RTN, or the register transfer notation. So the RTN, so it transfer between processor register and memory, between processor register and I/O devices. So the memory locations, registers, and I/O register names are identified by a symbolic name in uppercase alphabets. So the RTN, it is a way of specifying the behavior of a digital synchronous circuit. So in RTN notation, it is a way to describe micro operations capable of being performed by the data flow. You have the lock or location, place, mem or memory, or the address of memory location. Whereas the R1, R2, or processor registers, the data in, data out, or I/O registers. So it means that the RTN, so it is a way of, or it is a way to describe the operation, so capable of being performed by the data flow, data registers, data buses, functional units. So at the register transfer level of the design, which is the RT. So also describes conditional information in the system, so which cause operations to come about. So contents of location is indicated by using square brackets. So the RHS of RTN always denotes a values and is called source. So the LHS of RTN always denotes a symbolic name where value is to be stored and is called destination. So the source contents are not modified. Destination contents are overwritten. So examples of the RTN statements, we have the R2, location end, and R3 plus R2 is equals to R9. So in this statement, R2, R3 acts as a replacement operator. So this statement defines the transfer of content of register, okay, from R1 into register R2. So the R1 and R2, it denotes a transfer of information, or R2 and R3. Okay, so that's all for today, VC. So thank you for listening. Have a nice day to all of you. I'm Din Jane.